Hello guys, welcome back. We are going to solve our second problem in Otto Cycle. This time we're solving problem 153 and 154 because we're going to write code in ease. We have a 4-cylinder spark ignition engine that has a compression ratio of 10.5, and each cylinder has a maximum volume of 0.4 liters. At the beginning of the compression process, the air is at 98 kilopascal and 37 degrees, and the maximum temperature of the cycle is 2100 Kelvin. Assuming the engine to operate in the ideal Otto cycle, determine A, the amount of heat supplied to the cylinder, B, the thermal efficiency, and C, the number of revolutions per minute required for a net power output of 45 kilowatts. We're going to assume variable specific heats for air. Since we are going to use variable specific heats for air, that means that we will need to use our table A17. So let's just mark this. So variable specific heats. Variable specific heat is the clue, and when we are gonna let's change our color. This time will be a purple. So that means table A17. Okay, so this is pretty similar to the previous problem. So we're going to start as usual with our PV. Let me change them. It changes the color of the highlighter, not the color of the pointer, so you can tell the difference between one video and the other, even if it's only the so we have again our compression, heat addition, expansion, heat rejection, and the same for the TS diagram. We start with isentropic compression, constant volume heat addition, isentropic expansion, constant volume heat rejection. And we know this is (98 kilopascal, 310 Kelvin, and 2100 Kelvin. Okay, just to summarize what we know from the problem, we know that we should use variable specific heats, that means table A17. We have a compression ratio of 10.5, a maximum volume which is equal to V1 of 0.4 liters, which is 0.0004 cubic meters. We know that the net power that we have is 45 kilowatts, and 4 cylinders, and of course we are talking about an Otto cycle. We should know that because we already have these drawings. So we've been told that P1 is 98 kilopascal and T1 is 310 Kelvin. This defines completely state 1. T3 is 2100 Kelvin. So we are asked to find out the efficiency, the speed in RPMs, and Qin per cylinder. Okay, so we can recall from last problem that network was work in minus work out, and Qin is U3 minus U2. This work in is the work done from 1 to 2. And work out, the expansion work is U3 minus U4. If you don't remember how to get to this expression, remember this, all these three come from first law for closed systems. And you can look at problem 934 that we solved in the past video to check how to get to this. We also notice that we don't use CB delta T because we now need to use table A17, as we already mentioned here. So we have we can start by getting these parameters in order to compute our efficiency. Since our efficiency is W net over Qin, once that we have W net, we can recall that the power that the machine can develop is the network per cylinder times the number of cylinders times the mass of each cylinder. This network is the specific work, kilojoules per kilogram, times the speed. This speed is what we are looking for, and since it's RPMs, this is in kilojoules, we need two conversion factors. 1/60 is to convert from RPMs to seconds, to minutes per to seconds, and 1/2 is because we have 2 cycles, 2 revolutions per cycle. We need to solve for n. So how do we get the mass? Remember that the mass will be any volume divided by the specific volume. The only point that we have everything right now is volume 1, and we can use this because it's a closed system, so mass will be the same in each state. Volume 1 is already give it to us in the problem, but the specific volume we can get it from our ideal gas. So volume 1 will be RT1 divided by P1, and remember this comes from ideal gas. So basically we are ready. In order to get these values, we will need the temperatures. Let me swap a little bit to the tables. These are the tables that you have in your book. We are going to use table A17, heated gas properties for air. So we are gonna move there. You should get familiar to these tables. Okay, so let's have a quick, even though we already did it in one video, a quick reminder. We have temperatures, and those temperatures give us the properties: enthalpy, internal energy, and entropy. And two parameters that we defined as reduced pressure and volume, reduced volume. Notice that they don't have any unit because they are dimensional numbers. Okay, so we are going to use them. We can get really for the values for state 1 and state 3. So state 1, which is at 310, we can get the internal energy to be 200. Give me just 1 second. At 310, we have 221.25, and we're going to use reduced pressure, reduced volume, so that is 572. Now state 3 is at 2100, so we're going to get it right now, and we see that our internal energy is 1775.3, and the reduced volume is 2.356. So we have these values, and we can put it in our problem. They are already known. So state 1, E1 is 221.25, and VR1 is 572.3, while state 3, U3 equals 1775.3. This is kilojoules per kilogram, and VR3 is 2.356, no units. So how do we get the values that we need? We still need U2 and U4. Well, recall our isentropic relations for constant gas, for variable specific heats. We have VR2 divided by VR1 equals V2 over V1. We don't know these values, but we have that this number is 1 over R. So we can get VR2 to be equal to 500 VR1 times V2 over V1 is 1 over R. So substituting will be 572.5 times 1 over 10.5. This is 54.50. So we need to go to table A17 again and look for a value that is at least close to 54 for BR. So BR, here we have between 55.54 and 51.63, so it should be in the middle. Sorry about that noise. We keep going. So by interpolation, we finish with this and then we'll take a break. So T2 will be 765.31 and U2 will be 564.28. Three to 4, we know that BR4 divided by BR3 equals B4 divided by B3, and we can solve for BR4. We don't know BR3 before BR3, but we know that this is R. So substituting, we have 2.356 times 10.5, and this is equal to 24.738. So we go to table A17 and we are looking for the value of 24.73. So we look at this value, this column, and we notice that we can find our value between these two So the temperature will be between 1000 and 1020. So again, by interpolation, we find that T4 is equal to 1005.96 Kelvin, and U4 is equal to 764.05 kilojoules per kilogram. So we can now substitute and we have work out to be 775 0.3 minus 764.05. This gives us 1011.25 minus work in, which is 564.29 minus 221.25, 343.04 is this is work net, so 668.21. Now Q in will be 175.3 minus 564.29 will be 1211.01. So if we divide it, that will be our efficiency, 0.5518. So the efficiency of the cycle is 55.18%. Now, for the speed, we know that we need to get the mass. We have not done that yet. So the mass, said it will be the volume 1 divided by volume 1, and volume 1 will be 0.287 times 310 divided by 98 kilopascal. This is 0.9079 cubic meters per kilogram. Since we know volume 1, we can get mass. This is cubic meter divided by 0.9079 cubic meters per kilogram. So that is 4.406 10 to the minus 4 kilograms. That's our mass. So first we can compute total Q in for one cylinder. Times Q in, which was 1011.01. So Q in is this is per cylinder. Finally, we can get our speed. We can solve from this expression n. We are solving and substituting. Since we already have all the data, this is 45 kilowatts, which is kilojoules per second, times 60 seconds per revolution, seconds got cancelled, times 2 revolutions per cycle, divided by 4 cylinders, times 4.406 10 to the minus 4 kilograms per cylinder. This would cancel, times 668.21 kilojoules per kilogram per cycle. And kilograms got cancelled. So at the end we will have 4,585.6 RPMs, revolutions per minute. And okay guys, so that's it. Please watch the next video where we are gonna solve this same problem but using ease. Thank you.